are continuing on arithmetic for computers chapter. Done all of the integer arithmetic, addition, subtraction, multiplication, division. And we went over the basic design of an ALU. And last time we started by going over the floating point representation. And today we're going to cover these two operations in floating points. So how to do addition, how to do multiplication. So floating point precision, it's this relative precision based on the exponent bit, right? So all of the fraction bits are significant. And the number of decimal digits from a given number of bits is going to be given by this equation, where b is the number of bits and t is the number of decimal digits. And we went over the range of the single precision and double precision floating points numbers. So if you convert that to decimal digits, for around 6 decimal digits of precision with single precision, whereas with double precision with 16 decimal digits of precision. So we are going to talk about addition and multiplication in floating points, and because of that floating point, where the decimal can move around, the operations are going to be a little bit more complicated. So the first thing is overflow. This occurs when the number or exponent is too big to be represented. So if my 8 bits of exponent are not enough to represent the point where that floating point needs to be, then that's when I have overflow. And then I also have underflow when the number is too small to be represented. So it needs to be so close to 0, right? That again, my 8 bits of exponent are not enough to represent that 2 to the power of the negative number, then we have underflow. And accuracy can be a big problem depending on your numbers. Like if the mantissa bits or the decimal bits are too long, they can get truncated, right? You only have 23 bits. If it goes beyond that, like say it's repeating, then you are going to have some error. And there are different rounding modes to reduce your error if you know the distribution better. And then we also have things like positive divided by 0 is going to yield infinity. And there is a specific bit pattern for representing infinity, negative infinity. And then 0 by 0 is not a number. So like we talked about, not using a standard is even worse because of portability and just sharing code, but implementing this standard is a little bit tricky. But implementing any standard with floating points is going to be a little bit tricky. So here is our first example, and we're going to start with decimal, because just like with integer arithmetic, floating point arithmetic, binary decimal, it's the same process. So if we have these two 4-digit decimal examples, so 9.999 times 10 to the 1 and 1.610 times 10 to the negative 1. I want to add them. What's the first thing I need to do? We all know how to do this.
So move the decimal point properly and stack them.
Yeah. So align the decimal points. Which one should I align? Smaller one or the bigger one?
Smaller.
Yeah, smaller one. So the smaller one in this case is 1.61, right? So to align it, I'm going to move the decimal
That's my dog.
to the left, right? By how much? Yes, 2. So let's do this. Step 1, align the decimal points, right? So shift the number with the smaller exponents. In this case, we shifted 1.61 to the left by 2. And now they have the same exponent. And once they have the same exponent, I can just simply add them, right? I'm gonna add the significance. And then we get 10.015 times 10 to the 1. And what is usually done at this step, because usually this is not how we would finish this. So we're gonna normalize it back, right? So to normalize this back, I have to move the decimal which way? So do I increase or decrease the exponent?
Increase.
Yes. So we're gonna normalize the results, and we're gonna check for overflow / underflow. This isn't the case if you're doing paper math, right? I can just add more digits as needed, but in hardware, we have that fixed amount. So let's say that we were stuck with just the 4 digits. We have 1, 0, 0, 1. We can't hold this 5. What does this one become?
2.
Yeah. So we would round. Okay. So round and renormalize if necessary. And the reason we renormalize is because if you round at the bottom, it can ripple all the way to the top and then round the top one. So you might need to renormalize after. But that would be a edge case. So now we're going to look at this 4-digit binary example. So we have 1.000 times 2 to the -1, and we want to add -1.110 times 2 to the -2, and then it's converted to decimal here, just so that we can double check our answer in the end. So first step is. So which one are we going to shift?
The negative. The right one.
Oh, yeah. Yeah, the negative number one, and then which has the smaller exponents. So we need to move it by 1, right? So we shift the number with smaller exponents, right? So this one stays the same. This one gets shifted by this much. Just once to the left, and then we adjust the exponents. So now they have matching exponents. And when they have matching exponents, we can again just add the significance. In this case, it turns into a subtraction. We know how to do this from previous lectures. So we would end up with this number here, 0.001 times 2 to the -1. Next step is normalize it, right? So we have to move the decimal over by 3. And then because of that, we are subtracting 3 from here. So we get 2 to the -4. And here we had 4 binary digits. Here we can still represent 4 binary digits. There's no need to round or truncate. So there was no change. And then if we convert this into its decimal counterpart, we get 0.0625, and we can double check that that is correct from here. So floating point addition is just the same as decimal addition with floating point number. Here is what the hardware looks like. So this small ALU is just going to basically take the subtraction of this exponent and this exponent to find the difference, right? And then based on the difference, whichever one was smaller, that's the one that we are going to then shift the exponent of. So this control decides which one gets shifted, right? Because we have these, the fraction here, and it goes here, and this fraction goes here as well as here. So whichever one is determined to be smaller by this ALU will get input into this shifter, whereas the other one will be input just as it is. That's decided with these two maxes. And then after it's shifted to align with the larger one, this big ALU just does the addition, right? And then here, we are going to normalize if we need to normalize. And then here we are rounding if we need to round. And we get the exponents and then also the fraction and the sign bits comes through as well. So we can see how this hardware looks a little complicated, but it's all just doing the same steps that we just did. So here is your first full question. Your code is, I believe, 132. Yep, 132. So do this one on your own first. Most of us are done with this. We are not quite at the threshold to skip the peer discussions to go over it with people around you. Time for your discussion.
Okay. Answers that I don't know and how horribly mistaken.
At first, I was like,
Yeah,
but
but
like,
what-
like colors were fine, like,
And,
and then when you enter into it, and then you shift it like level.
And you should normally use based
You
on
wanna
this
make
one's
some
decision.
Yeah. Oh, you then move, yeah. Because those throws. You do that. On the as you know, okay, so you're like,
I'm not sure what this is. Again,
Oh.
probably for math. And so I need to study more.
Okay, to resubmit your answer if you. Right, so the first thing I just did is align that, right? So this one is smaller by 2. Right? So I need to shift it to the left by 2 in order to make it aligned with this one. So this one stayed the same, right? But the other one is shifted to the left by 2. And now I just need to add them, right? So 0, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, and then 1, and then 1, and then we have to remember this, right? So we're looking for this number, and that is it. Right? And then this set of slides and practice problems, we were just going over how to do the arithmetic math parts. But on your homework, you're going to be given the 32-bit representation of the floating point number. You have to convert it into this representation in its numeric form. And then when you do the math and you get the answer, then you have to convert it back into the 32-bit floating points form. And question 3 is the one that's floating points. So sometimes one common mistake is just students going through it and forgetting to read that it's floating points, and they just do the 32 bits addition. So do pay attention that the third question, both of them are floating points. All right, so floating points multiplication. Again, this is going to be the exact same process as decimal. So we'll start with decimal first, once again. So if I have 1.110 times 10 to the 10, then I want to multiply it by 9.2 times 10 to the negative 5. What is my first step?
I'm thinking into the fraction.
You could do that, but what is kind of the faster way?
Add the exponents.
Yes, add the exponent. So they have the same base of 10. And in binary, we have the same base of 2. So we can just simply add them. So our new exponent is just gonna be 10 to the 5. And then once I've dealt with the exponents, dealing with the decimal part is again very simple. Just multiply them, right? And then after we multiply them and we have this new exponent, the next step, this is not the exact final result. Next step is normalize it, right? So I'm going to shift to the left by 1, so I'm going to add 1 to the exponent. And then, yeah,
When you shift left with exponents, that's when you subtract, right? So
it
for,
depends what you're doing. So
is this
I'm
considered?
moving the decimal to the left here, right?
Mhm.
So I'm making the number 10 times smaller, right? So to adjust for that, I have to make the exponent 10 times larger, which means just adding to the exponent 1.
Is this decimal like base 10?
Yeah.
Okay.
Anytime you see it called decimal,
Okay.
that's base 10. Right, so we've normalized it, and we again have 4 digits, but our answer is 5. So what do we do with the, at the 2 and the 1 here? How am I rounding it?
Round down.
Okay.
Yep.
Okay, two.
Round down. So 1.021 times 10 to the 6 is our final answer. And we don't have to, well, we do have to determine the sign, right? If they were different, it would be negative. If they're the same, it's positive. In this case, they're both positive, so they're the same sign. So we give it the sign of positive. And then here is our 4-digit binary example. So 1.000 times 2 to the negative 1 and negative 1.11 times 2 to the negative 2. So the exact same example for the addition. Now we're doing multiplication. So first step is, once again, add the exponents. So my new exponent is negative 3, right? And then we multiply the significance. And if we multiply these out, we just get as 1.11, right? Because this is just 1, right? And then we have this as our result. Nothing to normalize, right? And then
we multiply the way we would for,
yeah, exact same way. Yeah. You just have to deal with the decimal, and the way you deal with the decimal is the exact same way as you do decimal. All right. So one thing that it does say to note is that in floating point IEEE format, we have the bias exponent, right? So before we even get it into this format, we have to subtract bias, right? So we can, once we have it in this format, we can do this, right? And just add that thread. That's when we have to go from here to back to floating point format, we have to add the bias back in, right? And then here we determine the sign, right? And they're different. This one's positive, this one negative. So we have a negative sign. So here's another example. We want to do 3 times 5. 1.1 times 2 to the 1. This is 3, right? 1.01 times 2 to the 2. This is 5, right? So we're going to add the exponents. We get 3. Multiply the significance. We're going to get 1.111. And then we're going to normalize the results. In this case, there's nothing to do, right? It's already in its normalized form. And then round and renormalize if necessary. And there's nothing to do here. if you were limiting yourself to a certain bit width, like if you only wanted to store 2 bits of mantissa, then you would have to round. And then your answer would change and your exponent would change, right? But in this case, we're not limiting ourselves. We're doing it by hand. We don't have a specific hardware for this. And then we just determine the sum. Okay? And then we can just double check our answer, right? So we have 1.111 times 2 to the 3. So we move the decimal to the right by 3. And then this is just 15. And then we can do 3 times 5. 3 times 5 is 15. Okay. So now doing multiplication, and then if you're given these numbers as the 32-bit number, right? So you have the sign, then you have exponents and mantissa. Here we see the mantissa is all zeros, right? Mantissa is all zeros. And if you convert these to decimal, subtract 127, you'll get 3 and 4. And we can also see that they only differ by 1, right? They're all the same except for the last bit. So again, I have the exponents. 4 plus 3 is 7. And then one thing that you can do is rather than convert both of the exponents by subtracting the bias from the both, is just work with it directly and know that if I add this exponent to the other exponent, the bias is doubled. So to account for that, I can just subtract the bias once. And now my new exponent is in the format that I needed. It has 1 bias added to it. So that's all it's saying here, right? So if we have exponents, is exponent 1 plus exponent 2. If we keep them exactly as they are, then when we add them, we have the bias twice. So we just need to subtract it once in order to get the exponent with the bias added in already. So here we are multiplying the significance and determining the sum. And once we have that, we can put our results back into the IEEE floating point problem. So floating point instructions in MIPS. So floating point hardware is not on the direct data path. It is a coprocessor because it's going to take longer. Right? If we put it on the direct data path, then we wouldn't be able to do other independent instructions at the same time while we wait for the coprocessor to do the floating point instruction. There are separate floating point registers. They're 32 bits single precision are these ones. And then to get double precision, you pair them together. So the first 2 go together, the next 2 go together. And floating point instructions operates only on the floating point register. You cannot use the normal 32 registers for floating point instructions. And this is fine because programs usually don't do integer operations on floating point data or floating point operations on integer data. And with more registers, we also have minimal code sets impact. And then we have these instructions for MIPS. So floating point load and store instructions. So load words that would load into the floating point register base. Okay. And then we have our different arithmetic operations. We have them for single precision and double precision. Okay. So we can add .s for single precision, add .d for double precision floating points. And with the single precision, you have all of the registers, so we use them individually. Okay. So this would be, the result goes into F0, and we're adding F1 and F6. With double precision, you're specifying the last register of the pair. Or I mean, the first register of the pair. So 0 for the first one, and then 2 for the second one, 4 for the third one. So all of these operands need to be even numbers. And then again, it would be into floating point register 4 and 5, multiplying floating point registers 4 and 5 by 6 and 7. Okay. And we need 2 registers because for double precision, we need 64 bits. Okay. And then it also has these comparisons. So the x-axis would just be replaced by the comparison that you want. Equal, less than or equal, things like that. So you can set these conditions for your branches based on comparing floating point numbers. So in summary, for the entirety of floating points, we have these bit patterns that have no inherent meaning, but with standards, we give them meaning. Right, we went over Foo's complements, and we also went over IEEE floating point formats. And then the computer instructions, along with the standards, determine the meaning of the bit pattern. And then because we are having like fixed hardware in order to do these operations, we have this finite range and precision in computing, with digital computing at least. So the computer arithmetic is going to be trained by this limit of precision. And then if you have overflow or underflow, and your program depends on precise results, you need to be able to detect those things. So for Friday, you do have reading for the next chapter. And the next chapter, we're going to finally start the data path of this. And like I mentioned, homework 2, you can do it now. You can finish the whole thing. So it's due before class Wednesday. So 1 week. Oh, the other thing is I did only upload the PDF. There were way too many submissions that did not follow the format of the homework, so I'm not doing the document.
There's no block on this.
I'll just ask the other people that are this one.
I don't
It's probably someone in a.
I was talking about for the starter.
Try to find the only like.
I'll show you. Those are the questions. See those.